Hello there, welcome to Chemistry Chapter 4, Lecture 1. In this lecture you're going to need your notes and your textbook, and that's about it, so you don't need a calculator today. So let's go through the notes. This chapter starts on page 99, and we will be going through On Your Own Problems 4.1 through 4.5. Okay, so we've got some definitions here. A pure substance is a substance that contains only one element or compound. So I gave you a couple of examples of what a compound would be that is also a pure substance. And an example would be sugar. So sugar, this is a sugar molecule. Sucrose, in fact. So that's an example of a pure substance that is a compound instead of a single element. Another example would be table salt, NaCl. So that is a pure substance that is a compound. And of course the elements would be anything off of the periodic table, the individual elements. Now, a mixture differs from a pure substance. It's a substance that contains different compounds or elements. So in a mixture, individual elements or compounds retain their properties. Okay? Mixtures can be physically separated, and an example of that, and one you're going to do in the lab, you're going to separate a mixture of sand and salt. So you can use a filter, all right, to separate a mixture sometimes. Pure substances, though, must be decomposed in order to separate them. Unlike where a mixture, you can use physical means, such as a filter or maybe boiling or something like that. A pure substance has to go through a chemical reaction in order to be separated. So we have a couple of different kinds of mixtures. There's a homogeneous mixture. Some people pronounce that homogeneous, either way. It's always the same no matter what part of the sample is being observed. So, for example, milk, hopefully that's just a white liquid, right? You don't have a lot of floating bits in that or something like that. Or salt water, you can't really see the salt in it. The salt is dissolved. Or lemonade is just a yellowy liquid, and there's not going to be any, you're not going to be able to tell the different parts of the lemonade. It's all just lemonade, but it is a mixture. In fact, air is a mixture. It's got oxygen, nitrogen, argon in it. So a mixture, but you can't really see those individual parts, can you? A heterogeneous mixture has a different composition depending on the part of the sample being observed. So if not all of this makes sense, there's a really good graphic in the book on page 104 where it goes through pure substances, gives examples, mixtures, the difference between an element and a compound, a homogeneous or a heterogeneous mixture. So look over this graphic on page 104. All right, 4.1, we are on page 106. So if you'll turn to that, we'll go ahead and answer these questions. And it says, classify the following as elements, compounds, homogeneous or heterogeneous mixtures. Okay, so copper would just be an element. Okay, carbon dioxide, and you can try to answer the question before I write down, see if you can get it right. But carbon dioxide, that's CO2, that would be a compound. All right, let's, I'm going to see if this will write a little smaller. I'll try the red pen here. Cake icing. Okay, so cake icing is going to be a mixture. Let's assume it's just like vanilla or chocolate or something like that. That would be a homogeneous mixture. Now you could have some cake icings where you could see different parts of it for sure. But in this case, we're just going to assume the simpler situation. A tomato, if you cut it open, you can see all sorts of different parts of the tomato. You can see the outer skin, you can see seeds in there. So that would be a heterogeneous mixture. Sugar water would be a homogeneous mixture. Sodium, that's just Na, that's an element on the periodic table just by itself. Fruitcake is a heterogeneous mixture. If you don't know what fruitcake is, you just cut into it and you can see the cake and a cakey substance and also bits of dried fruit. So that'd be heterogeneous. A lot of times it only surfaces during Christmas. Sodium fluoride, all right, sodium fluoride would be a compound. And finally, tap water, that is a mixture. It would be homogeneous. And that's because it is tap water, okay? It's not pure water, which would just be a compound. But tap water, depending on where you live, will have a lot of different substances in it. And plus, the water departments, localities add fluorine, they add chlorine, things to help your teeth get stronger or to kill bacteria. So tap water is not pure water. So it would be a homogeneous mixture. Okay, moving on down the notes. We'll talk about a chemical change. So a chemical change is a change that affects the type of molecules or atoms in a substance, such as burning wood. But write this in there, and I don't know if you can see that very well, but with a chemical change, write this underneath in your notes. A new substance is formed. Okay, so write that in. An example with a chemical change, you're going to have a chemical reaction. So if we have hydrogen and oxygen, you can make water out of that. So that is a chemical change. We originally just had a hydrogen molecule and an oxygen molecule, and then we ended up through the proper chemical processing made a water molecule from that, and that is a chemical change. A physical change is a change in where the atoms or molecules in a substance stay the same. So you're not getting a new substance. You're just doing something to the original substance. Maybe you're heating it up. Maybe you're changing its shape. Maybe you're dissolving it in water. Okay, that's a physical change. All right, so let's take a look at 4.2. And we'll discuss, this is on page 109, we'll discuss whether it is a chemical or physical change. So Part A says steam condenses into water. Well, it's still water. It's just that it goes from the gaseous phase as steam into the liquid phase with water. So that is a physical change. Still water. Now, gasoline burns in an auto engine. That's a chemical change. The gasoline, through the process of combustion, creates some new products such as carbon monoxide, carbon dioxide, nitrogen monoxide, nitrogen dioxide, some sulfur compounds potentially. So New substances are formed when gasoline burns an auto engine, and some of those substances come out the tailpipe. All right, a barber cuts hair. Well, it's still hair, it's just shorter. So that's a physical change. Milk sours, well, that's a chemical process. So the milk turns into something else through the process of digestion by bacteria. So milk souring, and you get the bad smell and a bad taste, but it's becoming something other than milk. All right, sugar dissolves in water. That's physical. We could separate that sugar back out. Milk poured on cereal, also physical. Still milk, still cereal. Don't make a new substance. An iron nail rusts. Okay, that's a chemical change. So we're taking iron and making it into iron oxide. All right, that's what rust is. It's iron oxide. So you're getting a new substance on the surface of that nail. All right, so that takes care of 4.2. Now let's look at the very bottom of the first page of your notes, and we'll go through So on your notes, this will be empty here. I know you can see it now, but phase changes. So I'm going to link a video in the description box for you to watch, talking about phase changes, but this is something you deal with, especially when you think of water. Solid, almost always the most dense phase. Not true with water, but with most things. If you heat a solid, it turns into a liquid. If you heat that liquid, it turns into a gas. And a gas is the least dense. Going in the reverse direction, a gas can be cooled into a liquid, and then a liquid can be cooled into a solid. So when we go from a solid to liquid, we call that melting. When we go from a liquid to a gas, we call that boiling. So go ahead and write this in your notes over here. A gas to liquid. All right, we call that condensing. And then finally, liquid to solid. We would call that freezing. All right, now a lot of times we use those terms mostly with water, but it works for any substance. Okay, let's take just a second and we'll erase this. And then pause the video if you need to catch up. All right, and we'll move on. So, if you go on to page 2 of your notes, let's take a look at 4.3 in the book. So, on your own, 4.3, we are on page 111. And that one says, cubes of frozen alcohol are put into liquid alcohol. Will the cubes float or sink? Well, alcohol isn't water. And most substances, the solid is more dense than the liquid, and that's true for alcohol. So will it float or sink? All right, so it will sink. All right, the way that water freezes in that crystalline structure, there's a lot of air gaps in that, and that causes the solid version of water to be less dense than the liquid, but that is not normally the case. All right, let's take a look at 4.4. That one says natural gas companies store most of their natural gas in liquid form rather than in its gas phase, even though they must deliver it to the customers as a gas. Why do they do that? Well, natural gas, there's a storage issue here. So if they will condense it to liquid form, and they usually do that with high pressure, the liquid version of natural gas takes up less space. All right, so that makes it easier to store. When it's delivered to you, it's delivered in the form of a gas, but as they are storing it, they can store a whole lot more in those big tanks. Maybe you've passed by a natural gas storage facility, big tanks along the side of the road. They are stored under very high pressure, and that causes the gas to be in liquid form. All right, so almost done with this lecture. We'll talk for just a second about the kinetic theory of matter. I'll have a video linked in the description box for you to watch, just a very, very short video. And the kinetic theory of matter is that molecules and atoms are in constant motion. The higher the temperature, so the higher the temperature, the greater their speed. All right, so that probably makes some amount of common sense to you. So let's look at on your own, and you can, it's important to read the chapter here at the beginning of chapter 4 because we're not really doing a bunch of math. So make sure you look at figure 4.4 about the three phases of matter. So 4.5 says if a substance is cooled down 10 degrees, will its molecules be moving faster or slower, and will they be closer or farther apart? Well, they're going to move slower. So we're on page 114. They've been cooled down, so they're going to move slower, and they will be closer together. So you cool it down enough, they'll make a solid, and then the molecules are very close together. Okay, the last thing to talk about in this lecture are the homonuclear diatomic molecules. This is important for tomorrow's lecture where we're talking about balancing equations and predicting chemical equations. And homonuclear diatomic molecules are elements in nature that are composed of two atoms instead of individually, and you've got to memorize these. So it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. They all appear in nature as a homonuclear diatomic molecule, all right, meaning there are two. Okay, so looking at your periodic table, there's a pretty easy way to memorize this. So you've got to remember hydrogen is a homonuclear diatomic molecule. And then all of the others make a 7. Okay, so it's a 7 that starts with 7. So nitrogen, oxygen, fluorine, and then they go down like that. Okay, so fluorine, chlorine, bromine, iodine, astatine. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine. The 7 that starts with element number 7. And then you can't forget hydrogen. So that's an easy way to memorize the homonuclear diatomic molecules, and you will absolutely have to do that and need to do that. All right, that does it for this lecture. You can answer a lot of review questions on this homework. So you can do review questions on page 131. You can do 1 through 9. You might have to read the chapter. So we're going all the way through, let's see, you'll want to read all the way through page 115. And then you can do 1 through 4 and read page 99 through 115. And then we'll get into balancing chemical equations and predicting chemical equations on the next lecture. So the classic vinyl of the day, put this into view, is a band called Asia. All right, pretty good album that came out in 1982. I will link that in the description box if you are interested in listening to it. Quite a few hit songs on that album. So give it a try while you're doing your homework and see if you like it. All right, talk to you next video.